All right, I'm looking for something about Gaussian curvature in a article called Differential Geometry of Surfaces. And in particular, it is in curvature of surfaces in Euclidean space, which gives me a function z equals f of x, y. And really, once we have that z of f of x comma y, this is not the same x comma y described here because we're rotating that so that the tangent so that the x and y here is a different x and y. However, they don't use that same math down here where they calculate this p, q, f, and r. I figured out in another video that did not get saved, unfortunately, so I can't show it to you. But what I did was I kind of figured out a way of getting this p and q is to say we're going to take f of x comma y, which is our z, and figure out del x comma y of f, and it comes out to be del f del x and del f del y. You could put a z in here, del f del x, y, and z, but that would just be 0. So that is what's defined down here as p equals f of f sub x, p, and q equals f sub y, q. So I'll just go ahead and put that in there. And notice I've got kind of a sideways sense to the vectors here. I'm also going to put over here another form that will be del x, y, z going down, which will yield an r, which is del f del x, an s, a del f del x del y, and no, this was not r, this is t right here, and this is s, and this is also s. And then if we did the z's, they would just fill out with zeros too. I guess there's one little ambiguity though here, because what is del f sub z, or del f of x comma y del z? Well, it depends. Do you think, well, I guess it doesn't really depend. It's 0. It's definitely 0. But what's the Jacobian of the Gauss map? If you've got that 0 in there, then definitely this thing, the Jacobian of the Gauss map, is going to be 0. If you don't, if you imagine a 1 there for some reason, though, then the Jacobian of that would be the same as the Jacobian of just those terms. Okay, so I'm curious, or I'm not sure. Let's make sure this is not the Gauss map, not Jacobian of Gauss map. What is the Jacobian of the Gauss map? We'd have this because this is not f. The Jacobian of the Gauss map. This is the n. This is the Jacobian of the surface. Or no, it's not even the Jacobian of surface. It's the Jacobian of the gradient of the surface. It's a nabla dot nabla f, whatever you call that. It's the Jacobian, the divergence of the gradient of the function f. And I'm not even sure how you determine what is the gradient of a function in the z category when you know that it is perfectly flat in z. So actually, it would be kind of be described by a Dirac delta function in that form. And I'm going to put a question mark around that because it would just have a value at, or it would just be there at, no, it would be a height. Height. No, I don't know. This is the trouble with losing a video. Okay, anyway, when we do take the Jacobian of this, which is called the Gauss map, we do definitely get some quantities up in some places and then all zeros down here. So to say that this is the Jacobian of the Gaussian curvature is the Jacobian of this thing, it just doesn't work out. However, well, it would just be nice to see the derivation of this thing. It seemed to work, but I'd just like to see the derivation for it. Anyway, okay, Paul Gradenwitz says, I think we're pretty clear about what is parallel transport. I say, no. Soon as you call something that is obviously not parallel, you're being deliberately unclear. So I should think in some detail. Of course, we do parallel transport of a vector. No, not around a sphere, you don't. A vector comes in two kinds. One vector is defined by two sets of coordinates, which would be like x0, y0, and x1, y1. The start point and the end point. Another vector is defined by one set of coordinates, a direction and a scalar length. Like what? x0, y0? I think you're being, and uh, what? Uh, r, theta? Sure. But that's just x sub naught plus r cosine theta and r sub naught plus y r cosine theta sine theta. I don't think you guys have thought sufficiently about vectors. So when you say that I have not, it's ridiculous. Why I say scalar here, because I want to make clear that this vector not automatically has units of length that are space units. Okay, because what? Because they could be velocities, or they could be electric fields, or because they could be magnetic fields, they could be gravitational fields. Yes, you can have scalars. You don't necessarily have, yeah, they're called differential path. There's differential path vectors, which are displacement vectors, and there's other kinds of vectors that are not displacement vectors. Right. Maybe the word scalar is not the most correct. I think the word you're looking for is displacement. But I hope you understand. Now, the parallel transport of this vector is only related to the base coordinate set. The base coordinate set of Euclidean coordinates would be x, y, of course. The angle is kept the same with respect to the metric of the space it is in. So your correct observation that a rigid body cannot have parallel transport of all its points is different from this issue. Also, I agree that two great circles are only parallel at their largest separation point of 90 degrees from their intersection points. So meridians are parallel at the equator. Okay, so this is pretty significant here, because if he says, I agree that two great circles are only parallel at their largest separation point from at 90 degrees from their intersection points, and then he say, we do parallel transport of a vector. Actually, those two statements are not consistent, because if you have drawn, if you've drawn, I don't know if I'm making a semantic argument or just talking to myself, but if you've got it so you have a vector going from here to here from two great circles, and you want to parallel transport it, say that way or that way, you can't, because these two great circles are only parallel at that point and that point, where the angle between them is 90 degrees. Now, you could almost parallel transport it by moving it just a little ways, but you can't parallel transport it. You can't move it at all, and keep those two ends at the same length. And that's kind of the point I was trying to make. And then Paul made a funny joke about the color of a polar bear's skin rather than the color of its fur. A map that is used in navigation has a very special declination spacing. In Dutch, that is called vergrotendbreed. It gives a translation of the declination phi to y coordinate in nautical miles as y equals 10,800 pi natural log pi over 4 plus phi over 2. On this map, every loxodrome is a straight line. So a loxodrome, he said, was an angle that kept a constant heading. So like this guy would be going northeast 45 degrees. And if he kept going northeast 45 degrees, kind of spiral around the Earth until he reached the center, I guess. The center or the North Pole. And he says that on this map, every loxodrome is a straight line. So I would guess that you can only map a portion of the sphere with this map. Yes, it does appear that this website is in, I guess, Dutch. I wonder if there's a way to translate it. It looks like there's a little button up here. Maybe it'll work. Yep. The increasing width or increasing width meridional parts is the increasing width or maps that use a non-parallel projection. The scale increases as the distance to the tangent point increases. In order to calculate the loxodrome between two positions, the increased width difference del/b is used for loxodrome navigation. Well, that looks kind of cool. So yeah, 10,800 pi natural log. Whoops. Yeah, he's got tangent there. I left out the tangent. Natural log of tangent. Natural log of tangent of pi over 4 plus phi over 2. And it's also divided by pi. On this map, every loxodrome is a straight line S. When he sets a straight line on that map from point A to point B, let's say from point A to point B, it will actually probably follow some kind of loxodrome, which will be a line of constant heading. It is not the shortest route, but the most easy to sail with only a compass. Right, that's pretty cool. After this detour, we might see that the parallel transport means we take a vector and move the vector along a line that is defined as straight. I would just say we move an object, we move a point. We're not really moving a vector. We're moving a point. The point is we're taking that compass, and moving that compass from point A to B, and the sides of the ship don't necessarily stay like solid. in this coordinate system. So in that coordinate system where the compass gets to follow a straight line, the actual boat, if you looked at the shape of the boat, if you had a big boat here, it would, in that coordinate system, it would like not look like it was shaped right. It would be warped. But in the boat maintains its correct shape in the Euclidean coordinate system. So this Vergrotendbreit coordinate system is really handy for using a compass, but if you want to represent the shape of a boat, it doesn't, and keep it rigid, it probably won't keep that boat rigid. If once you draw this Vergrotendbreit coordinate system flat, it's not going to make that ship look right. All right, I think I'm going to make another video straight away, so I'll say ta-ta for now, but I'll be right back.